With that, I want to welcome everyone to this webinar today. I'm Teresa Schell, I'm Head of Policy at Chemsec, and I'm really happy to welcome you to this webinar in our series, where we look into details of the availability of alternatives for PFAS for specific uses. So we choose topics that are of special interest in the discussion of the universal PFAS restriction process. And if you want further details on the process and the dossier, we have other webinars and analysis available on our website. And the recording and slides from today's webinar will be made available, and be sure of that. So today we will take on a specific area of the F-gases uses, the use in mobile air conditioning. We do this for two reasons. Firstly, it's because F-gases in general are responsible for 63% of all PFAS emissions. So restricting this use is of absolute highest priority. And secondly, we recognized during a previous webinar that we had that there is a special interest for this particular use. And for those reasons, we've invited 3 company representatives today, and we will also get a presentation from Chemsec on the topic. So I'm very happy to present the panel that we have lined up for you. We have Felix Novak Valenta, Test Engineer Systems and Vehicle Testing at Volkswagen. We have Dr. Roman Hecht, Global Chief Engineer for Natural Refrigerant Systems at Hanon Systems, and our own Cecil Dirscher, Senior Policy Advisor here at Chemsec. And for the Q&A session, we also want to welcome Karsten Wachmutz, specializing in research and development for thermal management of electric vehicles at Volkswagen. And as I already said, after the presentations, we will make everything available, and during the webinar you can post questions in the Q&A box here in Zoom, and we will try to answer as many of them as possible. So please make sure during the presentations that you write down the questions in the Q&A box. So thank you very much for that. And with that, I want to welcome our first speaker, it's Cecil Dirscher here from Chemsec. She's a senior policy advisor with a long background from working for national authorities on REACH and its implementation. And at Chemsec, she is not only specialist on the REACH legislation in general, but also our dedicated representative in the ECHA Socioeconomic Assessment Committee, SEAC, with a depth of knowledge in PFAS uses and alternatives. Cecil, the floor is yours.
Thank you very much, Teresa, and I'm happy to be here. And I would just like to give you a little bit of information about the universal PFAS restriction and the problems also that we have with F-gases, just to give you some context about why we are talking about F-gases in mobile air conditioning. So if I can have the next slide, please. So the universal PFAS restriction is certainly the biggest and most wide-reaching restriction that has ever been proposed in the EU. It covers the so-called forever chemicals, the PFAS, that are called so because they don't break down in nature. They're very persistent. They are also sometimes called the all-over chemicals because we find so widespread contamination. And you can see a summary of the restriction proposal that was proposed from 5 member states of the EU in order to tackle this crisis that we have with the PFAS. So it's a restriction of the manufacture, placing on the market, and use of PFAS. It follows the scope of PFAS from the OECD definition, which is very wide scope of more than 10,000 substances, including the F-gases, but also fluoropolymers and other F-gas substances. In the proposal, there are several derogations proposed. There are 20 proposed derogations and 26 potential derogations, which are the potential derogations are for those uses where the authorities thought that they would need more information from industry to justify that there were no alternatives available. But basically, This proposal covers all sectors, and all the derogations in the restriction proposal are based on whether there are alternatives available or not. So next slide, please. Yeah, I tried to put up a tentative timeline for how the proposal from the 5 member states could be handled according to those procedures that we have in the REACH restriction. And if you start from left to right, you can see that the proposal was sent to the European Chemicals Agency, ECHA, in the beginning of 2023. And there was a public consultation on the proposal from March to September. I guess a consultation that many of you know about, and maybe you have also provided answers to the consultation. But while the consultation was running, the ECHA committees, the Risk Assessment Committee and the Socio-Economic Committee, SEAC, started to develop their opinion on the proposal. And they are still working on that, while the member states that submitted the proposal are working on a revised proposal based on what came in from that public consultation. They are working on it. They meet 4 times a year. Next meeting, end of November, they will discuss, for example, construction products. But they have actually also said that F-gases will be one of the next sectors to be discussed. So actually F-gases might be discussed already at the meeting in March. And continuing the work, going through all the sectors, at some point, maybe it could be end of 2025, the Risk Assessment Committee will have their final opinion on the proposal, and SEAC will have a draft opinion. And that will then be a consultant for that opinion for 60 days. And based on that, SEAC will develop their final opinion. And those 2 opinions and revised proposal will be sent from the Chemicals Agency to the Commission. Could be maybe in 2026, you could say this is a hopeful timeline, and that's also why I have put question marks there. But so you can take it like it's a possible timeline. But then when ECHA has sent it to the Commission will look at all the documentation and they will develop their own proposal, which will then be sent to the member states. And if they vote on it favorable, the restriction could enter into force 2028, 2029. So anyway, all in all, you can see that if you are a company working with PFAS, you might need to have a PFAS-free solution on the market already around 2029, while if you have a use that is derogated for 13 and a half years, it might not be until in the 2040s that you would have to be able to market the alternative. But the best advice, of course, is to start working now. And of course, the longer the authorities use in their work, the longer companies will have in finding alternatives. Yeah, next slide, please. Just a few words about what is the problems related to F-gases. Many of you probably know that originally F-gases were mostly a climate issue and an ozone layer issue. We had the Montreal Protocol, we had the Kigali Amendment included there. The recent F-gas regulation are all based on concern for the climate. But what happened then was that many of those F-gases with a high global warming potential were substituted with the so-called HFOs, which have a low global warming potential, but unfortunately they form TFA. And now we find TFA, increasing level of TFA in surface water, groundwater, and drinking water, widespread contamination, and increasing levels. And we also have more and more scientific evidence that these substances are problematic. They are very persistent, they are very mobile, they have reproductive effects and accumulate in plants and so on. So that is why we really have a need to move away also from these substances and switch to the natural refrigerants. So next slide, please. These are just my final points. I participated in a big event about mobile air conditioning in Berlin in September, and learned some key points, I think, about the issues we have around PFAS and mobile air conditioning. I learned that there are definitely two refrigerants that are possible alternatives to CO2 and the propane. But I think it's also important to say that the CO2 seem much more advanced than the propane. I also learned that it's easier to switch to natural refrigerants in electric vehicles than it is in combustion engines. I don't know why, but there may be some technical problems. Also important to say that, of course, aircon is not the only use of PFAS in the car industry. You will also find other PFAS uses in that sector, maybe in different components like O-rings and surface treatment, transport, refrigeration during transport, and so on. But the focus of this webinar is the aircon. And most importantly, and finally, I found that much work is going on to find alternatives to the F-gases in mobile air conditioning, and that is also why I'm really excited to hear the next speakers, to hear about how they have handled this issue. So looking forward to that, and saying now thank you from my side.
Thank you so much, Sissel. And again, I want to encourage everyone to note down any questions that you have in the Q&A so that we can pick them up when we have the Q&A session at the end. So that brings us to the next speaker, and that is Felix Novak-Valenta. He has a background from biochemical and mechanical engineering and is currently working on test engineer systems and vehicle testing, specializing in development of refrigeration systems and heat pumps with refrigerant R744 for automotive applications at Volkswagen. So please go ahead, Felix.
Thank you for the kind introduction. Yeah, so I think we can already jump to the next slide. So what we want to start off with is here, you can see the 12 cars from the VW group, so not just VW, but also Audi, Skoda, Cupra, whatever, that you can buy right now in the market. So these are already established. Maybe you've seen some of them in your neighborhood or on the highway. And of course, these cars are only going to get more, right? So we're looking at the MEB 21, which is the last line of this slide. So the Cupra Raval, VW ID2All, the smaller cars, all of those are also going to be equipped with a R744 system and with a heat pump with that refrigerant. So this is serious production technology. There's no magic about that. It's already available and it's on the streets in the hundreds of thousands. Next slide, please. So with that being said, I would like to kind of move up a little bit in what we're talking about. So if you are looking at thermal management, I like to focus on the three main bubbles in the middle of this slide. And I would like to call them our customers, basically, as thermal management engineers. So we've got the high voltage battery in an EV, the passenger compartment, and the drivetrain and electronics. And all of these three customers have thermal management needs, right? They want to be cooled, they want to be heated, some combination of that. And to move the heat from one of these components to the other, we installed circuits, so not electrical circuits, but like refrigerant circuits and cooling circuits. So there's some hosing that is being run through the car to move heat energy from one place to the other. So for example, in the wintertime, there's still some excess heat from our drivetrain. The drivetrain doesn't need it. We can catch that, we can take that and supply it to the passenger compartment, which is a very efficient use of energy, right? So we use the thermal management, so all of these components to move heat from one place where it's not needed to another place where it might be beneficial. I'm not going to go into details on the operation modes on the right-hand side. That is just some eye candy if you have any questions about that, about all the stuff that this system can do, because it's quite complex, but also very capable. I'm happy to go into detail in that with the Q&A session. The main item of this slide is that the choice of refrigerant is quite important, right? So the physical properties of a refrigerant define on how your thermal management works. Yeah, next slide, please. And that's why you need to choose wisely. And we chose R744, as has been said before. So what's our motivation to go this way? Because at least for heat pump systems in a car and a mobile application, that has never been done before. So we chose R744 because of its environmental compatibility. So it's a very good refrigerant in that regard. As you can see, I think you can faster read that, or maybe you already know all these facts, then I can tell them to you, but it's not a PFAS, it doesn't form TFA, doesn't have a global warming potential basically, and doesn't really have an ozone depletion potential. And on the other hand, it's a very good, R744 is a very good heat pump refrigerant. So you can use it to very low temperatures and you can still collect heat from the outside air, and you can help your battery electric vehicle especially to gain some range in comparison to traditional systems that can't go below -15, -20 degrees, which CO2 can. Of course, where there's benefits, there's also challenges, right? So its physical properties make it so that you need a very high operation pressure with CO2 systems, so R744 systems, and also high operating temperatures. That's just the physical items that we have to deal with that come with R744, and those force you to choose the materials respectively. So you need to choose materials that can withstand the pressures and the temperatures, of course. And with CO2 being a tiny molecule under a lot of pressure, leakage is also a challenge that you have to overcome. So also you need to choose your materials wisely so that the leakage rate is okay, that you can keep the refrigerant in your refrigerant circuit. Next slide, please. So if you think back 2 slides ago, we've seen it from a very like a top-down view, so a very broad overview of a thermal management system. If you look at this on the right-hand side, it's a little bit confusing, but that's what we work with every day, basically. So this shows all refrigerant lines, coolant lines, all components, everything that makes the car go thermal-wise. On the right-hand side, everything in green is our refrigerant system. On the left-hand side in blue and orange, that's our coolant system. And where they interact, we are able to exchange heat energy from the coolant system to the refrigerant system or to the outside air, for example. Yeah, so we can jump 1 slide further, please. So if you go 1 level deeper or into the 3-dimensional world, back from this topology overview, you can see our MEB platform on the right-hand side. So that's our rear-wheel drive design on the top, and the all-wheel drive design on the bottom. The only difference being there's another motor on the front of the car, and we can collect the heat of both of these cars, of these motors, right? So we can use the excess heat to heat up our interior of the car in winter operation. On the left-hand side, you can see an animation. I can only highly recommend to check out the configurators of our MEB cars. There's very nice videos here. I would have liked to include that here, but in my experience, that makes streams like these very jumpy. So feel free to check that out. But you can see the collection of the outside energy, so warmer air, although it might be very cold. We can pack that energy into our refrigerant, pump it to the inside of the car and release it on a higher temperature level, so we can collect the energy from for example, from the driving motors and from the outside air. Next slide, please. So one of the misconceptions when you talk about R744, as I've said, the challenge of high pressure, people think, oh, you need massive refrigerant lines. You need a lot of metal. You need to, for 130 bars, which is the highest pressure that we run at R744 systems, compared to approximately 30 bars that we run at R1234YF systems, it's 100 bars more, right? So 100 bars, that's crazy lot. So people think you need a lot of metal to like keep that system intact. And as you can see here, we went to our workshop. We chopped these lines in half, and they are the same function, right? So each line in this picture does the same job in a conventional and in a natural refrigerant R744 system. and the line thickness for the metal part is identical. It's the same all alloy, it's the same thickness. So that's really a misconception. It's not a fact. Of course, you need to put some know-how, some knowledge into the hose part of the refrigerant line. So you need to know what you're doing, but also that is a challenge that has been conquered many, many years ago. Package-wise, on the right-hand side, you can see a R1234YF compressor on the left and a R744 compressor on the right. They are similar in power and capacity in what they can do power-wise in the car. And they have the same size, right? There's no package penalty for your engine compartment by switching to R744. It's the same. You can use the same package restrictions and no problem at all. Okay, next slide, please. So coming to an end, we have a lot of very experienced, very good international suppliers, right? They are the backbone of every OEM is a good supplier. So we know that the knowledge is out there in the market. Many companies know how to work with R744, how to design R744 systems. This design know-how is really widespread in the automotive supplier base. And we know of very many market-ready designs that have been presented to us because, of course, suppliers approach us and show us their new ideas, and that we were not able to bring into market, to bring into fruition, right? But that we know that are there. And that's just what we can communicate. We can highly encourage everyone to check that out because there's really a lot of good ideas out there in the market. Thank you so much for listening.
Thank you so much, Felix. And I see that you've already started to put the questions in the Q&A box. Perfect. Keep on doing that, please. When I hand over to our next speaker, it's Dr. Roman Hecht. He is Global Chief Engineer for Natural Refrigerant Systems at Hanon Systems. Roman has studied mechanical engineering at RWTH Aachen in Germany, followed by a PhD in thermodynamics of regenerative heat pumps at University in Dortmund. He started his professional career developing advanced heat pump system at Wiesmann in 1993, and that for the last 25 years he develops in various roles systems and components for AC and heat pumps for automotive applications, especially for e-vehicles at Hanon Systems. Go ahead, Roman.
Yeah, thank you very much for the introduction, and also thanks, Felix, to your presentation about the vehicle situation of R744. I would like to present to you in the next few minutes some more details about the components. A few of these R744 components inside of the MEB are developed and produced by Hanon Systems here in Europe, developed in Germany, in Kerpen, and production in south or east of Europe. Next slide, please. To start with a picture, one of these nice vehicles of VW now here shown with an R744 system, which of course is inside of this small engine compartment. I would like now to jump on the next slide to share with you the details of the Hanon Systems R744 content, which we brought in production in 2019. And if we now jump on the next slide, please, we would like to start to explain you more about the compressor. Felix already explained us that the compressor looks similar than a compressor, which is a YF compressor. So from the outside, only some experts can see what is the difference between the R744 and the YF. From the package, there is no big difference. The R744 is getting even a little bit more smaller because of the small displacement. The high suction pressure, which we have for CO2, helps us to have even high density. So with this a smaller compressor, in this case, for example, we are talking about a 5 cc compressor, which has the same performance as the 33 cc compressor of an YF. version. So that means we have a much smaller displacement. We are also using stroll technology here in this compressor for the special challenges for the high pressure in the absolute number. So if we talk about, for example, in a relevant full performance AC condition, we are talking about 35 pounds the suction side and 125 pounds the discharge side. So that means we have something on 90 bar pressure difference between in and out. So this, of course, takes also some special efforts in internal leakage or sealing inside the stroll. And for this, we have also developed some radial and axial compliance technology to have best efficiency and at the end, also an extreme robust operation. This CO2 compressor has an outstanding NVH behavior. It is better than the YF version because of the specific design and material which we have chosen for the CO2 compressor. This have even a better NVH behavior, even if the pressure is higher. It is optimized and developed for heat pump operations down to -30 degrees C. And just probably one comment, in addition to what Felix said before, that the compressors from the package side, the CO2 compressor looks similar to the YF. This story even will be better if we go to bigger compressors. So if we talk about CO2 compressors, which are the same capacity than, for example, the 45 cc or 57 cc, the CO2 version will be the smaller one because we are only increasing the displacement by 1 or 2 cubic centimeter. Please take the next slide. Second component, so after compressor, of course, for a heat pump system, it is very relevant to have valves inside the system. And we saw from Felix before the schematic where we had already some idea that it is to get all the functional modes realized was needed to have certain valves. This expansion and shutoff valve technology is developed by Hennes Systems. It is a bidirectional expansion or shutoff function. In this double block housings, we have always 2 valves inside. The valves are capable to be fully opened. We spend special efforts on externally, but also on internally leakages to avoid efficiency reduction because of any bypass, which we don't want to have. There is an internal self-calibration for the actuator to the valve so that we always have a position feedback inside the valve, which makes it very robust in the application. This MEB system, which is used by, or the application is running by VW, have 8 valves in, so that there are 4 valve blocks, which is each of 2 valves. You see on the left side, they are arranged inside the engine compartment. Next slide, please. An additional component, which is probably new if we talk about AC systems in the vehicle. It is not really new because in the past, the mobile air conditioning world was very familiar with accumulator systems. And later on with the TXVs, we changed over to the high pressure accu or refrigerant storage systems. Now back with CO2, we are preferring to jump on accumulator systems so that we have a low pressure refrigerant storage, and Hennes system integrated in this accumulator also the internal heat exchanger, which is for CO2 helpful for high ambient temperatures to get performance and efficiency in place. And with this component having this integrated in the accumulator, this won't cause extra lines and no extra efforts in the engine or in the vehicle assembly process. This accumulator have an excellent liquid separation and storage function included. Next slide. Also the gas cooler in the front, so it is a direct system which is here applied, so direct system to the ambient. The gas cooler is a 3-pass design with thermal barriers inside with an effective thickness of 12 millimeters. It is directly in the front of the vehicle and can be used as a gas cooler in the AC mode, as an evaporator in the heat pump mode. Next slide, please. Beside of all the handling system components inside this R744 vehicle, Felix already mentioned there are also other suppliers involved. You see here there are more components, especially in the HVAC and also the line routings, which is relevant. So there are also other suppliers involved in this. So it's not only handling systems. And in addition, and also this was mentioned before, we see that the global supply base for R744 systems for mobile air conditioning systems is now growing very fast. So there's a big interest on the supplier area to be prepared for R744. So it seems to be that there is an understood market for this. Next slide, please. Yeah, just to give you an idea, we named this slide that there is a large field experience. So it is much more than a field. So we are running now in the meantime more than 700,000 vehicles. Of all this 12 vehicles, Felix presented us in the first slide. So this is something which is a real market experience for this AC and heat pump system since 2020. And it's running very well, very robust, so without any critical failures in this last years. So from this, a real good field experience with R744. Next slide, please. Yeah, summarizing from our point, we see that PFAS-free AC systems for electrical vehicles, including heat pump function, they are already in the market. They are realized with R744. And as mentioned, the global supplier competition is growing. So this is always good for our technology if there are more than a few suppliers getting in this, so that it's not just good for our customers on the cost side. I would also name this as an engineer that is good that we have more heads thinking about more optimization and doing this, improving the situation. What we see is the R744 system shows very full heat pump capabilities down to minus 30 degrees C, with all this positive impact on the mileage range at these low temperatures. And on the other hand, we also see that R744 delivers the sufficient AC performance even at 45-degree ambient conditions. So that means, and please go on the next slide, we see that R744 is an all-rounder refrigerant for MEC systems, and we don't see any reasons to continue with chemical refrigerants inside these electrical vehicles. Thanks for your, jumping on the next slide and get back to the campsite.
Thank you so much, Roman. It's really interesting to see how this works in several parts of the supply chain. So with that, I want to thank all the panelists for your presentations and invite you for the Q&A session. And at this part, we also want to welcome Karsten Wachmuth, who specializes in research and development for thermal management of EVs at Volkswagen too, in case there are questions that he could answer better. I think it's a good idea to have as many experts as we can on these panels. I don't know, Karsten, if your camera could be put on. That'd be great. And thank you. We have received a number of questions, so I'll have a look here. The first question was actually to our ChemSec representative, Sissel, and it's a bit a complex question, but to summarize it, I think the question is about TFA And is it really toxic? Is it really a problem? I would summarize it. Could you please elaborate on that?
Yes, thank you very much. Well, I can say as much that the problems with TFA is a new one, so you could call it maybe an emergent issue because it has developed due to this increasing use of the HFOs. And we see now increasing the concentrations in water and other biota is increasing, and it's more and more widespread. And at the same time, of course, we have scientists studying this substance and finding looking at the toxic effects of it. And what we find now is it's different toxic effects. I mean, it accumulates in plants. That has been known for a long time, but recently Germany has actually looked at the literature and presented some classifications for it. They suggest it's VPVB, as we know, very persistent, very mobile. They also say PBT, and then they have found reprotoxic effects, so developmental disturbances, and also some problems for organisms that live in water. So I would say we know that there has been questions earlier about how problematic this substance is, but unfortunately, we only find more evidence for the problem than less. So I think, that's more or less the question I would see.
Yeah, thank you so much, Sissel. I think it's important to talk about this issue. So thank you for elaborating on that. So then we have a more general question about the uses of the carbon dioxide solution. Are these solutions, the natural refrigerants in general and this one in particular, also available for other vehicles such as buses and trains? I don't know who would like to answer that question.
Well, I can if there's nobody else.
Great. Thank you, Felix.
Well, we are not in that business, of course, right? We are doing passenger cars. But as we have been on the panel in Berlin at the Atmosphere conference, we have seen that there's quite a lot of solutions for R744 in the market for trains. I think it's more dominant that it's R290 by now, is what we've heard from Deutsche Bahn. But for buses, definitely R744 is quite a big standing.
Yeah, thank you for clarifying that. I also have a specific question for you, Felix, but I think others can answer it as well, but it's directed at you from the person asking. And it's, do the heat pumps in the electric vehicles have other PFAS uses, for example, PTFE-coated electric wiring? And we've heard of other examples. So I think that's a very relevant question.
So as we've seen, as I said, we were at the very interesting PFAS-oriented Atmosphere conference in Berlin, and we've seen that Obrist, which is like an engineering powerhouse or whatever you want to call it, so they do engineering for other companies. They disassembled compressors from our R744 system or from the MEB system, and they checked for O-rings with a PTFE or PFAS content. And what they've seen, and maybe Roman, you would like to take over, is that they found, I think, 2 grams or 3 grams in the compressor. I don't know about the other components. But what we've seen is that our suppliers approach us directly and they tell us, hey, in this part, we are using a PTFE part, for example, but we are already looking at alternatives and we could use this and that, but we need like this many months and that testing to bring that to fruition, to put it into the market.
Roman, could you maybe elaborate on it as well?
Yeah, I think in the development phase of this R744 components, of course, we focused on getting, even on the component level, rid of all the PFAS relevant components. What we have today is in the compressor, which we have in the market, is, as Felix mentioned, sealing or which is have PTFE in, so there is a small amount of less than 2 grams. But an alternative solution is in progress to be validated. So this will change in the future, and I'm not aware of other components which have still a PFAS content in. And of course, we need to have in our minds that of this, I would say, solid binded PTFE inside of a PTFE, or PFAS inside of a PTFE is something different than the gas version of a refrigerant. If we talk about something about 600 or 800 grams, or even 1.2 kilograms of YF inside of a heat pump system in an e-vehicle with YF. So I think we need to be a little bit careful how we compare here apples with pears. But of course, the intention should be to get rid of all PFAS component inside a CO2 compressor and the other components, yes.
Yeah, thank you. Then I have a question here. Why is R744 more effective in electric vehicles than in gasoline-powered cars? Roman, would you be able to answer that? Maybe I put you on the spot here.
There are 2 points which I would mention at first. I think the one is, of course, electrical vehicles are more needed to have a heating functionality because combustion engines have more or less enough heat, waste heat to heat the cabin. They only need some supplemental heat. So with this, you need a heat pump system which works down to minus 30 degrees. This is something which is not possible with a YF. So that means you need to have an electrical heater and you can have a small heat pump for the area down to minus 10 or minus 15 degrees. So you have extra equipment to get in for this. CO2 will be a cost advantage because you get rid of the electrical heater. And the second point, why we mention this for especially e-vehicles, it is, I would say, technically, for the state of the art where we are, given that we have electrical compressors ready or in market for CO2, to have mechanical compressors, if we have a poor combustion engine, we would need to solve the external leakage situation for the shaft seal. And this is something which is a challenging exercise and so far not yet finally in. So I think we recommend to start with CO2 in the electrical vehicle area. And for Europe, I think this will be also the solution for the future, understood.
And please help me, have I also understood it correctly that you need a larger amount then of refrigerant in an electric vehicle than in a combustion engine, if you just generalize it?
Yeah, if you generalize and say, okay, we would need to have a heat pump system inside an e-vehicle, and you solve this with an YF version, you will increase the amount of YF which is needed for one vehicle. And with this, from our point of view, we will, or you will increase the difficulty for PFAS because we will have more PFAS emission, more PFAS risk in the environmental if we change all combustion engines now to YF heat pump systems. So this will be something which makes the difficulty even larger, or the issue even larger.
Exactly. That's what I thought. Thank you. And that's a very important point to make, I think. Here's a question to Volkswagen, and it's quite technical, but I think maybe you can answer it. How much is the range benefit from R744 HP versus R1234 YF systems at low temperatures, like minus 20 degrees, and during an average use at moderate temperatures? Would you be able to answer that?
Yeah, I hope so.
Okay.
So if you check out the configurator for our cars that I mentioned earlier, you see that there is an option to turn on the heat pump and turn it off, and that is actually quite a complex topic. The question in itself is simple, but the answer is quite hard, because what we've learned is it depends on your battery size for one. So if you have a bigger battery, of course, you're driving more kilometers, and there's like a percentual gain of the heat pump. So it's going to be more kilometers the more you drive, the more efficient the car is, the less energy you use for actually driving, the bigger percentage of the total consumption is heating. in an electric vehicle. So the more efficient the base car is, the more better, the more important the heat pump is, basically, because you get more range out of your battery. And so if you turn to the configurator on your webpage, you can toggle the heat pump option on and off, and you can also toggle your driving profile. So what temperature? So basically exactly the realm of this question. What temperature are you driving at? Are you driving at city speeds, highway speeds, rural areas, whatever, a lot of stop and go? And that will give you an efficiency gain or a kilometer gain for that driving situation that you find yourself in, or that will be your daily commute to work or whatever. And you can see a kilometer value in that. It's not easy, and it doesn't really make sense to give a very specific, like X, Y kilometers will be gained. That doesn't make sense, because it always depends on the car, the battery, the driving cycle, the temperature, and all that. So it's a very complex question. And the best that I found is to look at the configurator and try to find your usage scenario and get the answer in a kilometer form.
Yeah, thank you. Even I understood that, so great. I got one question that I found interesting. Is there any associated risks with potential flammability in comparison to the R1234YF? Who could like to answer this?
To be honest, I did not get the question.
I'm
Flammability
assuming.
of YF, or what is the question about?
I think if you compare the two, is there a problem with flammability with the carbon dioxide solution? I suppose that is the question.
I have never seen R744 burning.
No.
Because this is something which, it can't burn. So there is nothing which can...
R744 is being put into fire extinguishers.
Yeah.
To extinguish fires. So.
Yeah, I guess the person asking is comparing with the propane problems. So that's why. Thank you. Then I have another question that I personally found interesting. Does R744 require special procedures, equipment for vehicle air conditioning maintenance? Is there a difference there?
Yeah, there's just as if you own a vehicle workshop, just as you would have had to switch your service station from one chemical refrigerant to the other, you will need to have a special service equipment, either a fully automatic one, or there's also like manual ones for smaller shops that don't do this that often, where the time benefit of an automated machine may be not that important. But you will need definitely like a service unit or some adapters to handle these pressures and to handle the different oil and all that. Yeah.
But there are no special requirements on the workshop. You do ventilation or something like this. So you just need the other machine, and that's it for the workshop.
Right.
Okay. Great. I've looked through the questions and we've answered most of them. So unless anyone would like to add something, I would like to just conclude a little bit from all the discussions we've had today, all the questions and the presentations. I personally learned a lot, so found it very interesting. So when I think about this issue, I mean, the phase out of F-gases is crucial to address the PFAS pollution crisis, and mobile air conditioning is one component in this use category. So I think we really need to think about all these different use categories. It's very important because they are so different. I mean, it's part of the green transition that we talk about all the time, and a potentially exponential use then, both due to the prognosed increase of electric vehicles replacing the combustion engine fleet, but also, like we talked about, because of the amount used for each vehicle would then increase. So it makes it even more important. So for every electric vehicle that doesn't have a PFAS-free solution, the implications are much more severe. And as we can see, we already have working solutions on the market rolling on our highways today. I seem to recall that Roman said 700,000 of them, to be precise. So there are more technologies under development that can broaden the choice even more. But based on the market situation that we have today, we shouldn't wait to substitute F-gases in mobile air conditioning for electric vehicles. We should substitute it now because it's really that simple. And with that, I want to thank you all the speakers today. Great presentations, and encourage everyone who attended today to keep an eye out for our upcoming Beyond PFAS webinars with more companies and solutions to be presented. So I hope to see you all then, and thank you very much for today. Bye-bye.